Independent events. So we're nearing the end of our first chapter, and I'm going to study in this lesson the probability of calculating independent events. Okay, so this means if the occurrence of one event has no effect on the occurrence of another event, then the events are independent of each other. Okay, so there's a special rule for this, so the product rule for independent events, and that is if A and B are independent events, then the probability of both occurring is given by the probability of A and B, which is the same thing as saying the intersection of A and B, and that probability is equal to the probability of A times the probability of B. Okay, so keep this, consider or compare this with what we did in the previous lesson. We were looking at probability of A or B, so one or the other event happening. But this time we're looking at what's the probability of both events happening, probability of A and the probability of B, and assuming that both events are independent. Okay. So let's look at an example. So a coin is tossed 4 times and it turns up heads each time. What is the probability the fifth trial will be heads? Okay, so each coin toss is independent of the others. So although we may think heads has to come up sometime, there is still only a 50-50 chance, or a 50% chance on each independent toss. So the important thing about probability is that probability has no memory. So you could flip a coin and get tails 20 times in a row. It does not mean that the next time you flip the coin, you'll be guaranteed heads. There is no memory. You have a 50-50 chance no matter what coin flip you're doing to get a heads or a tails. Okay, each coin flip is independent of each other. So therefore, the fifth toss has a 50% probability of getting heads. Okay, so part B, find the probability of tossing 5 heads in a row. Okay, so that's a question that you can ask. So it's the probability of the event is getting heads. So heads and heads 5 times in a row. So I'm going to express this using this kind of a statement. So 5 H's, 1, 2, 3, 4, 5. Okay, so that's going to equal the probability of rolling a heads times 5. I mean, like 5 times. The probability of rolling heads, probability of rolling heads times the probability of rolling heads times the probability of, or flipping heads, I should say. And each time each coin toss is a 50-50 chance. So 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which is 1 out of 32. Okay, so and as a percentage, you can express this as a percentage, 3.1%, and so therefore there is a 3.1% chance of getting 5 heads in a row. It's a very small chance. Okay. A coin is flipped when a die is rolled. What is the probability that you will flip a tail and roll a 4? So what's the probability of flipping a tail? So P of the event T is equal to 1/2, T for tails. The probability of rolling a 4 is 1 out of 6. So the probability of rolling a tails and rolling a 4, flipping a tails and rolling a 4 is equal to the probability of flipping a tails times the probability of rolling a 4, which is 1/2 times 1/6, and that's 1/12. Okay. So therefore, the probability of tossing tails and rolling a 4 is 1 out of 12. So the thing to keep in mind is that these are independent events. Flipping a coin and rolling a die, they are independent events. I'm not saying one depends on the other. These are completely independent. So if I want to find the probability of rolling tails and a 4, then I can easily just multiply each individual probability like we just did here. Okay. Example number 2, it's prom time. Tenzin's friend assures him that if he asks Michaela to the prom, there's an 85% chance that she will say yes. If there is a 60% chance that Tenzin summons the courage to ask Michaela to prom, what are the odds that they will go to the prom together? So the question has two events here. So we're going to say let A be that Michaela says yes. And let event B be the probability that, or the event that Tenzin asks the question. Okay. So the probability that Tenzin asks the question and Michaela says yes. So the probability that Michaela says yes, and the probability that Tenzin asks the question, that's what I'm looking for. Okay. And so that's equal to the probability that Michaela says yes times the probability that Tenzin asks the question. And so probability that she says yes would be 85%. So as a decimal to 0.85 multiplied by probably the probability that he asks the question, which is 60%. So that's 0.6. And then multiply those two together, 0.51. So there is a 51% chance that they'll go to the prom together. But the question does not ask for the probability, it asks for the odds. The odds that they will go to the prom together. So odds 4, not against, but 4. So odds 4 is equal to the probability of A and B divided by the probability of A and B prime, the complementary. Okay, I can rewrite that as the probability of A and B divided by 1 minus the probability of A and B. So in other words, basically, what's the probability that they both go to the prom together divided by the probability that they don't go to the prom together. And that's pretty simple. Okay, so that's going to equal 0.51 in the top. And if it's 51% chance that they go to the prom together, then it's a 49% chance that they don't, because the probabilities have to add up to 100. So 1 minus 0.51. And so that's 0.51 over 0.49. Or I can just say 51 over 49. But cut off at the end. So my concluding statement would be, well, yes, the odds, therefore, the odds for them going to prom are 51 to 49. Okay, so that's just a little question that revisits the topic of an odds and how does it connect to conditional probability. So this is a topic of conditional probabilities. It could be condition. Independent events is what it is. Okay. Example number 3. There are two tests for a particular antibody. Test A gives a correct result 95% of the time, and test B is accurate 89% of the time. If a patient is given both tests, find the probability that both tests give the correct result. So the probability of test A is 0.95, and the probability of test B is 0.89. So he's going to be given both tests, the probability of A and B. So what's the probability that he will get a correct result either way? Okay. So I'm looking for that. So it's going to be the probability of A times the probability of B. I'm going to multiply 0.95 times 0.89. And that's going to give me 0.8455, or as a percentage, I can say 84.6%. And that's how we do it. So therefore, there is 84.6% chance that both tests give correct results. Before I continue, I'm just going to answer one question. Well, why is it A and B instead of A or B? Okay, so remember, it depends on the wording of the question. So the probability that both tests give the correct results. I want both the tests to give me the correct results, not one or the other. If I ask, well, what's the probability that this person has an antibody? So you could get it from either A or either B, then that question could be like an or question. But I want to make sure that the test result is correct using both tests. So I'm going to say A and B, and that's why we're using this kind of probability formula. Okay. So what's the probability that neither test gives the correct results? So the probability of A not giving the correct result is just 1 minus P of A. So that's 0.05. Probability of B not giving the correct result, that's the complementary as well. So 1 minus probability of B giving the correct result is 0.11. So the probability of A not giving the correct results and B not giving the correct results of the two complementary events is going to equal to the probability of complement of A times the probability of the complement of B. Okay, so 0.05 times 0.11, and that's 0.0055, very small number, which is a 0.55%. Okay, so there's a 0.55% chance that neither test gives the correct results. Now let me write that concluding statement. Therefore, 0.55% of the time, neither tests give the correct result. Okay. Part C, find the probability that at least one of the tests gives the correct result. So the probability of at least one test. Now that's going to be equal to 1 minus the probability that neither of the tests give the correct result. So if neither of the tests, if we know the probability that neither test gives the correct result, then I can find the probability that at least one of them. So at least one could mean one or both, right? So one or both. So I'm going to say here 1 minus 0.0055, and that's equal to 0.9945, which is 99.5%. Okay, so it's a much bigger number. So remember, part A only asks both tests giving the correct results. That's why it's a smaller number, 84.6. Whereas part C is asking for at least one of the tests giving the correct result. So there's a really good chance at least one of the tests will give correct result. All right, so example 4. Su Ling travels the same route to work every day. She has determined that there is a 0.7 probability that she will wait for at least one red light, and there's a 0.4 probability that she will hear her favorite song on the radio on her way to work. Okay, so what is the probability that Su Ling will not have to wait at the red light, but will hear her favorite song? So I'm going to say here that we're going to let A equal the red light. So A is the probability that she'll have to wait for at least one red light. And we're going to let B be the probability that she will hear her favorite song on the radio. So the probability of A is equal to 0.7, so 70% that she will have to sit at a red light. Then the probability of A prime, the event where she does not have to sit at the red light, would be 1 minus 0.7, which is 0.3. Okay, and the probability that she will hear her favorite song is 0.4. So what am I looking for? Well, I'm looking for the probability that she will not have to sit at a red light, so A prime, and the probability that she'll hear her favorite song on the radio, B. That's simply P of A prime times probability of B. 0.3 times 0.4. That's 0.12. So therefore, there is a 12% chance she will not be stopped, but still hear her song. Okay. Part B, what are the odds in favor of Su Ling having to wait at a red light and not hear her favorite song? Okay, so I need to know the probability of A, which is 0.7. I need to know the probability of not hearing her favorite song, so B prime, the complement. And so if it's going to be 1 minus 0.4, that's 0.6. Okay, so the probability of A and B prime is equal to the probability of A times the probability of B prime, and that's equal to 0.7 times 0.6, and that's 0.42. Okay, so if I'm looking for the odds again, so the odds in favor or the odds for, then I'm looking at dividing P of A and B prime divided by 1 minus P of A and B prime. And if I write that up here, it's going to be 0.42 divided by 1 minus 0.42. And that's equal to 0.42 divided by 0.58. Or I could say 42 out of 58. Or if I write that in lowest terms, 21 out of 29. So I'm dividing the top and the bottom by 2. And then I can write my ratio. So the ratio is 21 to 29. So therefore, the odds for having to wait at a light and not hear her favorite song is 21 to 29.